Okay, so before I start, does anybody have any questions? Okay, so the conversation will be shorter than usual, I guess, about hour and 15 minutes. So first of all, exam will be 5 questions, 20 points each, and you will have 100 minutes to complete the exam. So 20 minutes per question. No cheat sheets. I mean, just pen and paper. That's it. No other instruments. And if you are familiar with linear algebra, know how to evaluate circuits, and are familiar with measuring, the exam should be easy. So don't worry much. Since you have 20 minutes to solve each question, it is useful to remember certain formulas which will help you speed up your solving during the exam. So what I will do today is go over important formulas or identities which might be useful, and then we will look at 2 or 3 practice questions, and that would be it for today. So most important are the unitary operators. You should know the Pauli operators by heart. So the X Pauli operator, is 0, 1, 1, 0. Y Pauli operator is 0 minus I 0. And the Z Pauli operator is 1, 0, 0, minus 1. While solving problems, you need to do a lot of computation, like what is the action of X operator on certain state. So it is useful to directly memorize what happens on particular states that we usually use, like 0, 1, plus or minus, with action of these operators. So you know that if X acts on 0, what do we get? We get state 1. If X acts on 1, what do we get? 0. If X acts on plus, what do we get? 0 balance. No, maybe. We still get plus. Okay. And if X acts on minus, what do we get? Minus. Yep. Minus. Yeah, so you get a minus coefficient here. Similarly, if Y acts on 0, it's 0. We get phase of I and 0 and phase of minus I and 0. Okay. Maybe you guys compute what happens to the plus and minus state under the action of Y. Okay, what happens to 0 and 1 under the action of Z? 0, 1. Yeah, so 0 stays 0 and 1 gets a 1 stays 1 with a minus sign. Another operator that we use regularly, let's also see what happens to the plus and minus. So Z acting on plus state gives you minus, and Z acting on minus state gives you plus.
I think the y and for 0, that should be I.
Yeah.
One, yeah.
Okay, so another operator that we use is Hadamard, which is 1 over square root 2, 1, 1, 1 minus 1. So Hadamard acting on 0 gives you state plus. Hadamard acting on 1 gives you state minus. Hadamard acting on state plus, you know what it gives? What gives us? It gives 0 again, and Hadamard acting on minus.
1.
I hope you know how to compute these explicitly. So you just do matrix vector multiplication and you get a vector as the result. Another gate that we use a lot is the CNOT gate. So you know that whenever we talk about CNOT, we usually assume that your first qubit is the control qubit and second qubit is the target qubit. Whenever the first qubit is 0, nothing happens to the second qubit. Whenever your first qubit is 1, the second qubit is flipped. So 0, 0 will stay 0, 0. 0, 1 will also stay 0, 1. For 1, 0, the first qubit is the control qubit, so second qubit will be flipped and we will get 1, 1 state. And similarly for 1, 1, second qubit will get flipped and we will get 1, 0 state.
The last line for the CNOT.
Okay. Thank you. Now what happens to the Hadamard basis states under the action of CNOT? So I will just quickly go through the first one and then you guys can try to calculate the other three. So we will first calculate the vector for the plus plus state. So we know that the plus plus state is nothing but plus tensor with itself, which is 1 over root 2, 1, 1, tensor with 1 over root 2, 1, 1, which is equals to half 1, 1, 1, 1. Now, to calculate the action of CNOT, you just multiply the matrix of CNOT with the plus plus state. And you will see that we just get the same state back. plus state. Plus plus. Try to compute what happens to these states. So you might get a question like, this is a unitary. What is the action of this unitary on Hadamard basis? Hadamard basis are just plus and minus states. So you just take the plus and minus basis state and just calculate what happens to each basis state under the action of that unitary, whatever unitary is.
Do we need to perform repeated special explicitly or can we just find the cluster elements of 0 minus and then use the C not on 0 0 will always be 0 0? And
So yes, you can choose to compute however you like, whichever you are more comfortable with. You can just deal everything in bracket notation, or you can write matrix and vectors explicitly and then perform computation that way.
So matrix calculation is not compulsory to show. We can
Yeah, you can just directly work with direct notation.
It's also like I had friends that were constants. So like worst case I could have like either
So those who are calculated it, check if your answer matches. Now let's do a practice problem to see why it is useful to memorize what happens to these basis states. So the question is like this. What is the action of the circuit on the computational basis states are any states rectangle. And the circuit is a 3-qubit circuit where you have a C naught from qubit 1 to qubit 3. Hadamard on all the qubits, and then C naught from qubit 2 to qubit 1. So how we so first let's understand the question. The action on the computational basis states. So what are the computational basis states? All the possible states with 0 and 1. So for 3 qubits, there will be 8 states. If it was Hadamard basis, then those would be the plus and minus states. So one way you can approach this problem is calculate the matrix for whatever this unitary is. But you might wonder how can we compute the unitary matrix for a C naught from qubit 1 to qubit 3, because we know the C naught for qubit 1 to qubit 2 is that, but how do we compute for this? And there are ways to compute it, but it's way too lengthy. So it's easier to just check the action of this on individual basis states, and it's much easier if you remember what happens to all the basis states. So let's see what happens to the state, the first computational basis state 0, 0, 0. So this is 0, this is 0, this is 0. This C naught will not have any effect since the control qubit is 0. So after the first C naught, is C naught 1, 2, 3, the state will still be 0, 0, 0. Then the Hadamard will act on all qubits, which will make these states plus, plus, plus. Now, a C naught acts from second qubit to the first qubit. So second qubit is the control qubit and the first qubit is the target qubit. So what happens to a plus plus state? We have computed over there that plus plus state is invariant. So under the action of 1 from 2 to 1, the plus plus state stays plus plus plus. Now, let's do a non-trivial state. So you will have to do this for all 8 states.
We can use those results as fact in the exam.
Yep. You can just mention that this is the action of C naught on this state, and then just use it wherever you want. Yeah.
Thank you.
So let's see for a non-trivial case. So assume for the 1, 0, 0 state. So if your first qubit is the control qubit and now it's 1. So 1 being the control, it will flip the third qubit, which is the 0. So it will become 1, 0, 1. Now Hadamard will act individually on each qubit. We know that Hadamard on 1 gives you minus state and Hadamard on 0 gives you plus state. will be minus plus minus. Now, the action of C naught from 2 to 1. So our second qubit is the control qubit and the first qubit is the target qubit. So currently our second qubit is the plus state, which is our control qubit, and the target qubit is the minus state. And what is the action of C naught on this? Yeah, it gives you minus minus. So the plus state will become minus. So this will give you so just for your practice, try taking examples of 3 or 4 more basis state and see if you can work it out without doing any explicit computations, just by memorizing these facts.
It's one to that. It's not this.
can cross verify if you got these answers. 0 0 state goes to plus plus plus. 0 0 1 goes to plus plus minus. 0 1 0 goes to plus minus plus. 0 1 1 goes to plus minus minus. 1 0 0 goes to minus minus minus. 1 0 1 goes to minus minus plus. 1 1 0 goes to minus plus minus, and 1 1 1 goes to minus plus plus. Now the second part of the question: are any states entangled? Are any of these resultant states entangled? What do you think? Why?
You can present the tensor product.
Yeah, exactly. So these are already in a product form, in a tensor product form. This plus plus minus is just plus tensored with minus tensored with plus, which is by definition a product state. So if you see states like this, you can just directly conclude that it's not an entangled state. However, if there was some superposition like plus 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 some other state, then you would have to show that then you would have to check if they're entangled or not entangled, like you did in the homework. But if you see states like this, you can just directly conclude that they are product states, and the product states are by definition unentangled states. Now let's see things you should memorize for measurements. So you know that every measurement corresponds to a set of measurement operators. If there are k measurement operators, if there are total k measurement operators, then you have k total outcomes. Assume that your initial state that you are measuring for the measurement which corresponds to this set of measurement operators is psi. The initial state is psi. Then the probability of getting ith outcome from these k total outcomes would be probability of ith outcome is norm of mk psi, which is just psi mk dagger mk psi. And the post measurement state on ith outcome, this will be I. So whichever the measurement operator it corresponds to. The post measurement state will be given by this. Let's call the post measurement state as psi sub I. This is the state we get on the ith outcome. And this will be given by mi psi, which is your initial state, and the normalizing factor of square root of probability. So if you have some state psi, and then you do the measurement corresponds to these measurement operators, you can get state psi 0, psi 1, which would be m1 psi square root of p1 with probability p1. Similarly, you can get state psi 2, which will be given with this formula with probability p2, and so on. So you need to memorize this, because unlike what we saw before, if you know the matrix, you can calculate what happens to a plus state when applying a Hadamard or something. You can just do matrix vector multiplication, but you can't really derive this during the exam. So you must memorize these formulas.
I have a question
Mhm.
for the measurement state psi I. Is that the post measurement result, or is it just like a
Yes,
measurement
it's a post measurement state when you get outcome I.
result? You get
Yeah.
And when do you transform that into like the EI theta psi? Like, because I think for some measurements, the result would be e to the power of I theta times the state.
It depends on the particular initial state and the measurement operators that you are working with.
Oh,
That won't be true in general.
oh, no.
Yeah. We will do an example of measurements in the end, and you will see. That's not true in general, but yeah, sometimes you get a normalizing factor, which is just then. So sometimes you get like some a psi mod of a, and these are the complex number, and then you can just write e to the I theta psi. Yeah, but that depends on particular initial state and the measurement operators you are working with. So that's not true in general. Okay, so if you are given an initial state and given a set of measurement operators and asked to give the different outcomes, probabilities, and post measurement state, you basically have to compute just this. That outcome 1 gives you this state with probability p1, outcome 2 gives you this state with probability p2, and so on. And just compute each thing using these formulas. Now let's see measuring observables. So measuring observables is defined by a single observable, let's say O, which is a Hermitian operator. And every Hermitian operator has a spectral decomposition. So we can write it, this operator O, let me call it A to avoid confusion. We can write this as sum over eigenvalues lambda I and the outer product of the corresponding eigenvectors of that eigenvalue. So this outer product forms a projection operator, and then you can write this as lambda I. And now the measurement operators, the set of measurement operators for measuring observable A becomes these all projection operators. It would be P lambda 1, P lambda 2, P lambda n, where each P corresponds to a particular eigenvalue. And same formula is applied here for calculating probabilities and post measurement states. So the probability, this is the small p and this is a capital P. So this is a projector, this denotes probability. So probability of getting, let's say, outcome M would be given by norm of projector for eigenvalue M times the initial state psi squared. So psi is your initial state. So this will be just psi Pm diagonal Pm psi, and using the properties of projection operators, we can reduce this to just psi. And similarly, the post measurement state on outcome M, let's call it psi M, will be given by Pm times the initial state and the normalizing condition square root of the probability. So if you are given a question, measure observable, let's say A tensor B, and you have the particular observable, how do you calculate the probabilities and post measurement states? The first thing you have to do is determine the set of projection operators, and for that you need to compute spectral decomposition of the observable. So you can do that. You just have to do, you have a matrix, you find the eigenvalues, you find the corresponding eigenvectors, and then just construct the spectral decomposition. Or you can also just memorize spectral decomposition for mostly used matrices, which is poly X, poly Z, and poly Y. So poly X, the spectral decomposition for poly X is plus plus minus minus minus. So this is the projection operator P plus for the eigenvalue plus 1. This is the projection operator for eigenvalue minus 1. Similarly for Y, you can write it as I minus minus I minus I, where the state I is 1 over square root 1 I, and minus I state is 1 over square root 1 minus I. And the spectral decomposition of operator Z is 0 0 minus 1 1. is also useful to know the properties of Hermitian operators. Do you know the properties of Hermitian operators? What are the properties of a Hermitian operator or an observable? So first is it has real eigenvalues. Yes, who said? Yeah, what are orthogonal?
The
Eigenvectors, yeah.
eigenvectors.
Eigenvectors of a Hermitian operator are mutually orthogonal. And there is one more important property. The eigenvectors of a Hermitian operator forms a complete basis.
Under the special decomposition of X, what do you write for the outer product, outer product for the plus again?
The projection operator. So if you're measuring observable Z, here is a +1 value, and this minus you can write it as plus -1. So this is λ1 P1 plus λ2 P2 in this form, which is like this form. And then those P1 and P2 forms your projection operators.
This is suppose Z is our observable measure on.
No, you measure state psi. The initial state is the state you measure. So this is the initial state.
With the measurement operator Z.
No, the observable Z.
Oh, observable
The
measurement.
measurement
of the
operators
observable.
are these operators in the projector operators in the spectral decomposition. These are your measurement operators for measuring observable Z.
Okay, yeah, makes sense.
So you might be asked to measure, say, observable A, which is outer product 0, 0 on some state psi. So first thing you need to do for this question like this, where you are given an observable and an initial state, and you're asked to measure and calculate probabilities and post-measurement state. The first thing you need to compute is the measurement operators. So to calculate the measurement operators, we need to first get the spectral decomposition. So how do we get the spectral decomposition of this? Or is it already in the spectral decomposition form?
It looks like a spectral.
Yeah, it looks like, right? So this looks like A is equals to your eigenvalue is 1 plus 1 and outer product 0, 0, which is your eigenvector. It looks like spectral decomposition, but you cannot forget the fact that eigenvectors forms a basis, which means that if you have a 2 by 2 matrix, you should have 2 eigenvectors. If you have a 4 by 4 matrix, you should have 4 eigenvectors to form a complete basis. So which means that there must be an eigenvector with eigenvalue 0, which is missing. So there must be some eigenvector with eigenvalue 0, which is missing. How can we compute that? You can do the linear algebra way, you have the matrix, calculate the eigenvalues, calculate the eigenvectors, but that might consume time. You can use another property that eigenvectors are mutually orthogonal. So if the one eigenvector is for sure the zero state, what the second eigenvector has to be? Yes, but up to a global phase. So it can be, so this state could be e to the I theta 1. But you can ignore the global phase, but something you should keep in mind. So the spectral decomposition for this would be 0, 0 outer product plus 0 times outer product of 1, 1. So now you have outcomes plus 1 and 0. You have two outcomes and the corresponding measurement operators, your set mk is p0 corresponding to the eigenvalue 0 and p plus 1 corresponding to the eigenvalue plus 1, which is 1, 1 and 0, 0. And now once you have the project measurement operators, then whatever given state size, you just apply the formulas, calculate the probability, calculate the post measurement state, and that's pretty straightforward.
What's the significance of the global state again?
Global phase has no significance. You cannot measure it. So it's like an artifact of the mathematical model that we use. If you remember from the first division lecture, I said that we work with vectors in Hilbert space, but that's not the correct picture. The actual picture is rays in a projective Hilbert space. Then you don't get the artifact of e to the I theta, but it's difficult mathematically to work in that. So that's why we just bear with the global phase and work with vectors in an Hilbert space.
So it's simulated rather than the actual.
Yeah, but it's mathematically equivalent. You just get an extra artifact which is useless. It is also useful to have the ability of going from outer product representation to a matrix representation. So you can keep this in mind, that if you have a matrix A, B, C, D, you can write this in outer product form as A0, 0 plus B outer product of 0, 1 plus C outer product of 1, 0 plus D outer product of 1, 1. The way you can see is the ket goes on the row and the bra goes here on the columns, and then you can quickly see that this matrix element corresponds to ket 0, bra 0. This matrix element corresponds to ket 1, bra 1, and so on. So you might see given an operator M, which is 1/2, 0, 1 plus minus 1/3, 0, 1. So instead of wasting time to compute the explicit outer product to generate the matrix, you can just memorize this, and this is how you go from a matrix representation to outer product representation.
But how would you know, so suppose you're given just two items,
Mhm.
and how should we know if it's AB or AC or AD or like maybe BC? Because two of them is zero, right?
Yeah, so those elements are zero. So those matrix elements are zero.
But I was saying like, suppose we're only given two terms, one is half, one is a third, right? So A could be half, and B could be a third, or C could be a third.
No, so
Oh, wait, never mind. 0, 1 and 1,
Yeah.
0.
yeah. The outer products are clear, right?
Yes.
Okay. It is also useful to know dot products as well for the, which is the inner product for the basis states that or the states that we regularly encounter. So the outer product between 0, 0 is same as outer product between 1, 1, which is 1. Same for plus and minus states. The outer product of any vector with itself is 1 in normalized vector. Then the outer product of orthogonal states is 0. Calculate this. You can do these computations during the exam. It's just vector matrix or vector multiplication, regular dot product, but it will save you time if you just memorize these things. This should be 1/√2, this should be minus 1/√2. So the outer product between vector A and vector B is, so this is a complex number. So the outer product between B and A, the inner product between B and A is just the complex conjugate of it. And if you have inner product AB, BA, since this is some complex number, let's call it Z, and this then has to be Z conjugate. So then this becomes mod Z squared. So this is mod of AB squared. Okay, so let's take a 10-minute break. Be back at 3:10. We will do an explicit example of a measurement problem, and then that will be it for today.
Hello?
Yes. Can you say something, Michael?
Oh yeah, could you do the decomposition of zero?
Wait, let me increase the volume. Okay, say now.
Could you do the spectral decomposition of zero, of at 0, round 1? I mean, yeah, whatever. 0, 1.
I can't hear you properly, but let me see. Or maybe put the question in chat.
Okay, I'll just put like you did like 0, 0 for decomposition, but did you like 0, 1 instead?
Which
For the spectral decomposition of the observable 0, 0.
I'm sorry, I can't hear you. Maybe just put your question in chat. Okay. Yes.
What's this called again?
No, this is just an operator. It's a matrix. It's just an arbitrary example. Yes, yes, yes. So and you can then two-value matrix where you don't have a term for 0, 0 and 1, 1. So these elements would be 0. And can you tell me then where half and 1/3 will go? Half would be 0, 0, 1, half. Yeah, that's it. And you have this.
This is the recap of the whole.
Why is the measurement because have the same eigenvalue. So the coefficient in front of them is the same. If they have the same coefficient, you just lump it together.
Okay. Then wrong for
There actually are 4.
Yes, there are actually 4, but these two have the same eigenvalue and these two have the same eigenvalue.
Okay.
So that's why in total you have. We will do a similar example, exactly similar example.
The other question is on the special
Projective measurements.
projective measurements. I think it should be discussion of what it is.
Like 20 points.
Yes, yes, yes.
Right, I get that.
But उन्होंने एक छोटा सा कार्ड भी दिया था तो उसमें भी कुछ जगह लिखी थी कि आप
Probability will always be 1.
Oh, well.
You will always find probability to be 1. So denominator will always be 1.
तो मैं वो भी फोटो भेज दूंगा
Yeah, maybe think about it. We can talk it from after the session and try to solve it and see.
That's so hard.
So today we get better way to do this because I think in homework we did because
Was like for.
So the one like you said, one way is calculate the explicit matrix and then calculate the vector. And second way would be just keeping everything in the Dirac notation, which is the bra and phi,
I don't
and then just try to compute.
I'm not able
Get that. You will see in the example today.
I guess we should just
हाँ वो बता दिया
And then just compute what happens here.
सुबह तो ऐसे ही मिल रही
sorry
थी
the double
अभी मैं
This is the inner product. It's the norm.
oh this means your product
I think.
It doesn't it's the norm. So it's the square root of the inner product.
so it's just
This is kind of hard.
तो
oh,
45 के अराउंड
when you said that, we tried to for this one, it's just the simple.
I mean, I like it, yeah,
So,
That's most
so the way to calculate it is
yes, but these will be not cat.
那就是个没准
oh, oh, right, because this is, yeah, so.
做呀。
Yes.
So this one is.
Yeah, and then you just multiply out, then you will get many terms.
Oh, I mean, this is just one.
Yes.
Okay, thanks.
Okay, so it's like.
The delta 它意义
Yeah.
它和 project project 是必须是一样的。
Okay. I feel you.
我觉得有点奇怪，就是measurement observable projective measurement 算法。
It's like this times this.
Oh, that's. I like try to do this.
projective
अच्छा ये मैंने बाहर से तो देखा है
它都有那个
Yeah.
मैंने पढ़ा था तो उन्होंने भी ऐसा थोड़ा सा बताया
projective measurement 它的对对对，然后这个字它就有意思，对对对 measurement of observable 对吧？它反正是它反正上面写的是这样 measure。
No, so we literally like this times this plus.
But I don't know how
They're just straight numbers.
But if you look up the
这是第二个，还有是有俩呢，这个是20。
Negative zero.
मतलब गया ना डिफरेंस मतलब एक्चुअली आई थिंक बाहर से मैंने देखा
projective measurement 它说 P
मैं मेट्रो से जाता था
的 characteristic 就是 P square。
ट्रेन से उतरा देखा है इसमें थोड़ी एक बार गया था मतलब और इसके साथ चले जाता
How do we know what to do? So much.
And I feel like
मतलब अंदर ही अंदर देखा मैंने सिटी की बिल्डिंग
Yep.
Yeah. I think we're just like. So like, if they give us a measure like. So I'm sure it's because I said you could solve it
One
with the
half is because of the state normalization.
observable 是一个 characteristic based on like spin axis 的，它我记得它
Initial state 1 over root 2, right?
Oh, that's correct.
Yeah, so 1 over root 2 is on this side and 1 over root 2 on this side, so you have 1 over root 2 factor twice. So that 1 over root and 1 over root 2 becomes half.
So let's say if it's 1 over, I guess 8.
Yes. You will see exactly how it happens in the example.
And the second part was, I didn't really get how. I mean, this is just like the left hand side of the. But then this part is I thought maybe we substitute.
Sorry, that's.
So this is just from the fact that.
oh yeah, there's a final. No, it's just like it's like a leap. It's like
Okay, because when I saw
you
final.
have you guys have a final and a project.
I will have to read
Yeah, I remember that. Like we
I-
have.
maybe we can talk about that actually.
Because I never went to.
It's not just we substitute
Okay,
K for
thank God.
Yeah.
K for just.
I saw.
This okay, so this delta means that if I and K are equal, then it will be 1, otherwise it will be 0. Same for here, if J is equal to L, then it will be 1, otherwise 0, which annihilates the whole term.
I guess I was a little confused because I thought no matter what we said, like,
ये सबको यूज किया था
Yeah, like and the.
हाँ
Yeah, or like measure.
मतलब ये तो मैं बहुत ही गलत कंपैरिजन कर रहा हूँ बट मुझे याद दिलाती ना गुजरे ही गया था नहीं that was pretty good
No, cause like I was actually at a friend house and I don't know like
Okay, so before we do the last practice problem, let me just comment on eigenvalues for Hermitian operator. So if you have, let's say, a 4x4 matrix A, and it has eigenvalues lambda 1, lambda 2, lambda 2, lambda 3, corresponding to eigenvectors A, B, C, and D. If this is the case, then the way you will construct the spectral decomposition will be with respect to only the distinct eigenvalues. So the spectral decomposition for A, which has these eigenvalues and eigenvectors. So the eigenvalue lambda 2 is a degenerate eigenvalue, which is a repeated eigenvalue. So the way you will construct this, the way you will construct the spectral decomposition would be lambda 1 outer product of AA plus lambda 2, and there are two eigenvectors corresponding to this eigenvalue. So this will be outer product of BB plus outer product of CC plus lambda 3, and this will have three outcomes total. So measuring A will have three outcomes: lambda 1, lambda 2, and lambda 3. So remember to check for the degeneracy in a Hermitian operator. Okay, let's do a practice problem. So let's psi be an rectangle state. Measure observable X tensor Z and give outcomes probabilities and post measurement states. So how will you approach this problem? So the first thing which you should aim to do for any measurement question is to get the set of measurement operators. Now for an observable, you need to construct manually the set of measurement operators by constructing the spectral decomposition. So we know that for x, does anybody remember the spectral decomposition of x?
Plus plus minus.
Outer product plus plus minus outer product minus minus. And the spectral decomposition for z, 0 0 0 0 minus 1 1. Now we just have to tensor these together. So x tensor z is outer product plus plus minus outer product minus minus tensored with outer product 0 0 minus. Now you just multiply out everything, so you will have 4 terms in total. This tensor product with this, tensor product with this, it has a minus sign, so we will have a minus sign here. Tensor product of this with this has minus sign, so we will have another minus sign here. And tensor product of this with this, both of them have minus sign, so we get a plus. Then you can just use the property of tensor product and combine this and this and this and this and just write it like this. So let me quickly show you how we can simplify this. So if you have outer product, tensor product of plus plus, this will become this from the property of tensor product, that if you have tensor product of if you have, well, I mean, yeah, and then since this is outer product, you can just ignore the tensor, because outer product and tensoring ket and a bra is the same thing. So this is just and you can just simplify together and simplify the notation and write it like this: plus 0 outer product with plus 0. This is same as this term. So let's simplify everything. Now, does this look like spectral decomposition?
Without eigen.
I mean, you have the signs, so they can be plus ones. So you can see here, this has so this projector has eigenvalue plus 1, this has minus 1, this has minus 1, this has plus 1. So let's combine the same eigenvalues together. This has eigenvalue plus 1. This will have eigenvalue minus 1 and outer product of minus 0 and plus 1. So now, from this, you can conclude that, so now let's check if this is a complete spectral decomposition, or are there any eigenvectors missing with eigenvalue 0. So we have 4 distinct eigenvectors. So we are good there. But you should check that the eigenvectors are forming a basis. Otherwise, there are some eigenvectors with eigenvalue 0, which then you might need to compute. So now you know the outcomes now. You have 2 outcomes, +1 and -1, and the projection operators, the measurement operators. The measurement operator for eigenvalue +1 is this whole thing, and the measurement operator for eigenvalue -1 is this. So this is the P plus projector. This will be the P -1 projector. Now we have our measurement operators. Now all we have to do is algebra. Now we just have to do math using the formula and compute the probabilities and post measurement states.
The measurement set, the first line there should be plus or minus.
Oh, yeah. Thank you. Okay, I will do the calculation of probability and the post measurement state for the outcome +1, and then you guys try doing -1 on your own and see if you are able to do the algebra. So the probability of outcome +1, or let me just write as a subscript, will be given by formula psi, the projection operator for the +1 outcome, and psi. We just have to write it. This is our psi. So taking the dagger of this will give you 1/√2 bra 0 0 plus bra 1 1. Now our projection operator, the measurement operator for +1 outcome, outer product of +0 plus outer product of -1, and now the ket psi, which will be 1/√2 0 0 plus 1 1. Now this factor of 1/√2 and 1/√2, we can just pull it out and keep it outside as a factor of half. Now I won't keep writing factor of half, but remember that we have a factor of half on the outside. So now we just have to multiply everything 1 by 1. So let's multiply this to the whole bracket and this. So this would be So you will get 4 terms. This 0 0 multiplying the whole operator, this 0 0, then 0 0 1 1 1 1 and 0 0 and then 1 1 and 1 1. And now we just have to expand each term individually. I will just show you the first term, and then I hope you get the idea. So the first term, expanding out explicitly, will give us now. Let's look at this. So this is nothing but the outer product of inner product of 0 tensor 0 multiplied with plus tensor 0. Now this 0 tensor plus, this is 1 over root 2 if you memorize the inner product. And this, then you can pull this 1 over root 2 outside, then you have inner product of 0 and 0, which becomes 1. So this whole element becomes 1 over root 2. Similarly, this is also 1 over root 2. Now here, this is 0 tensor 0 multiplied with minus tensor 1. Now, this is 1 over root 2. Now if you pull this out, you have 1 over root 2, 0 and 1. But this is 0. So this whole term gets annihilated, this also gets annihilated. So in the from the first term, you get a factor of half. And then if you do the algebra, you will get similarly. So this term will completely go to 0. This term will also completely go to 0. From this term, you should get another 1 over root 2 and 1 over root 2. And don't forget the half from this and this that we have outside. So in the end, we get half times 1 over root 2 times 1 over root 2 plus 1 over root 2 times 1 over root 2. Which is just half. So the probability of getting plus 1 outcome when measuring the observable X tensor Z on state 0 0 plus 1 1 is half. Yes.
Oh, sorry, I think you mentioned it before, but where did the 1 over root 2 get pulled?
Okay, so this 1 over root 2 and this 1 over root 2, these are scalars. So we can just pull them out of the equation. So you have a 1 over half factor multiplied over here, multiplying everything.
Oh, okay.
1 over half. This is this 1 over half factor. Yeah.
So what's the rule for the tensor product between two outer products then?
So
How do we define it?
So you mean the tensor product of like this?
I know, like two, like A out, A cat, A
Oh,
bra, tensor with B cat, B bra.
Okay, so you have like this.
No, like B is a cat.
Oh, okay.
And C is a bra.
Okay. Okay, so this will be
So the outer product between A and B, can I understand it as a tensor product of bra and cat? That's not calculated.
I don't get your question.
Okay. Yeah, let me actually think about it later.
Okay.
Ask you later, yeah.
Okay. Okay, now that we have the probability, we can now compute the post measurement state.
So for the system of 2 qubits, if one qubit is if two for the 2 states how do you do that? if the first one or the second one of them is orthogonal, then the whole is orthogonal and the whole.
Yes.
Do we have to calculate the probability that it ends up in -1, or can we just say the two outcomes are +1 and -1 and their probability has to sum up to 1, so. it's
Yes,
one
you
half.
can do this because you know that you only have two outcomes.
Got it, yeah.
If you have three outcomes, let's say you have outcome +1, 0 and -1, then what you can do is calculate probability for this outcome, calculate probability for this outcome, and then just you don't need to calculate the probability explicitly for -1 outcome, you can just subtract this from 1.
Okay.
Yeah, you don't need to calculate it. But do keep in mind the number of outcomes that you have. You might not always have two outcomes, you might have more than two outcomes.
Okay.
So how can we make sure we don't have an outcome of 0 because we cannot determine by calculation?
Yeah, you just check if you have the complete basis. That is, do you have, so this was a 4x4 matrix, right? X tensor Z.
Yeah.
So do you have 4 orthogonal states?
For orthogonal states. Oh, okay, I see, yeah.
Yeah. So if you have four terms for a 4x4 matrix, then it's a complete basis. So there are no hidden eigenvectors with eigenvalue 0. Thank you. Yeah.
Make sure if we have k measure if we have k outcomes and then we will have k post measurement states. So at the first you mentioned that if I have 4, just like the example, if we have 4 outcomes but each 2 of them are the same, so we finally will just get +1 and -1, but actually there are 4 outcomes.
Yes,
So
I
we
mean,
cannot, so can we determine which post measurement states is that just based on the measurement outcome? Because maybe each outcome stands for 2 post measurement.
no. The post measurement states are for the outcomes because the outcomes determines your measurement operator. And every measurement operator will have a post measurement state associated with it.
Okay, so there's in last example, we just have 2 outcomes and 2.
Yes, yes, exactly.
Thank you.
So there are technically 4 measurement operators.
Yes.
Yeah, but 2 of them are degenerate because they have the same eigenvalues. So 2 operators share the eigenvalue +1, 2 operators share the eigenvalue -1. So you have 2 outcomes, you have 2 measurement operators, so you will have 2 post measurement states.
Thank you.
Yeah. So it's determined by the number of distinct eigenvalues you have. The number of outcomes are the number of distinct eigenvalues. Okay, now let's calculate the post measurement state. So let's say the post measurement state is psi sub +1. That is the state you get after measuring observable X tensor Z on state psi and you see outcome +1. Then what would be the state after the measurement? This will be given by the measurement operator multiplied with the initial state and the root the probability. We already calculated the probability, which is
1 of 2.
yeah. So let's compute this. I will keep the probability on the side for now, but remember that we have the probability in the denominator. Let's first compute the action of this projector operator on our state. So the operator, the operator that we have is
+0.
+0 +0 plus -1 -1. And now we multiply our state, which is 1/√2 +0 plus 1 1, and then we just expand. So we have this 1/√2 outside, and we also have in the denominator 1/√2. So this get cancelled out. So this then you just multiply this with this, this with this, this with this, and this with this, you get 4 terms. And then if you actually calculate it, or if you remember what we did while calculating the probability, this will go to 0 and this will go to 0, and this is 1 over root 2 and this is 1 over root 2. So the post measurement state you get is 1 over root 2 plus 0 plus 1 over root 2 minus 1. This is our post measurement state for outcome plus 1.
Isn't it minus?
Yes, you're right. Yeah. This will be minus 1 over root 2 and this will be minus. Okay, try calculating probability for outcome minus 1 and post measurement state for outcome minus 1 and see if you are able to do the algebra. If you get stuck somewhere, let me know if you need any help.
So do the Bayesian equality.
Similar to homework, maybe taking some, yeah, homework. Definitely do go through homework 1, 2, and 3. That would be helpful. नहीं तो रोजा नहीं लौटा दिया नहीं लौटाया
हो गया है। कहाँ यूज करते हो?
Slides too, so.
मेरे भी मैं भी काम
Right, so I don't understand the spectral.
मतलब ऑक्टा को मैं उतना नहीं करता हिट एक तरह से
No, yeah. Right, I get that, but then why would you add them? You have to get one off, to get one measure.
मतलब एक तरह से ये कुछ नहीं होगा
Right, so I understand that, but I think for some reason that's, I think that's what slides say.
इसकी वजह से
We just get probability for an outcome as 1/2.
वेट के
Oh, sorry, one.
मटेरियल्स
Sorry, no, so two, so you're right, it's two, I'm sorry.
Oh, yeah.
So this is a product measure. It's a product measure.
इसमें लिखा प्रॉब्लम सेट 4 तो हमको दे दिए
Right, and so you think. It's a product measure.
आधा सेमेस्टर बचा उसमें सिर्फ एक असाइनमेंट आएगा पूरे एरिया पे
So what see it's different. No, let's see, this is the set of the tensor product. It's not sums. So
कंटेंट जो बोल रहा है उसके हिसाब से अगर मैं बोल लूं
according to what you were saying, you would have to have 0, 0, 10, 0, 0 plus 1, 1, 10, 0, 1. Right, for positive 1 and 0, 0, 1.
इसका भी मैं हम लोग खोल के देखा उसका इसमें भी
Okay, sure, let's say it's.
एक क्वेश्चन उसकी जो एग्जैक्ट फाइल है ना
And the post measurement state, let's say psi sub -1 on outcome -1, this would be calculated like
So I completely think
the measurement
I think
operator
the
for
same thing is
-1 outcome multiplied to your stage
It's like if you
and
compare
then
this up, right,
normalizing
it's like
factor of the
it's
probability
the same thing.
and you should get 1/√2 minus 0 plus 1.
1 and minus 1, yeah. Right, so that's why.
This is one way to solve this question, just using the bracket notation. The other way, you can just write down everything as a vector and a matrix and then do the computation that way. So this computation will be a row vector, a column, a matrix, and then a row vector, and then you get a scalar.
Like, so.
You can computation like this, but since there are
misunderstanding.
so much arithmetic to do here, you are more prone to make calculation mistakes. And but still, whichever way you prefer, you can either compute everything in direct notation or use explicit matrix vector form. But yeah, that's it for today. You are free to leave. If you have any question, meet me outside.
I'm sure like somewhere else.
So you're saying, so that's just the convention of how it's done.
Oh, I